We are starting our very last chapter of the year. Yay! It's coming full circle. When you started chemistry, you started talking about isotopes. And remember, those are the atoms where we have the same element, so the same number of protons, but they have a different number of neutrons. So, for example, there are 3 different naturally occurring isotopes of uranium. We have uranium 234, 235, and 238. So this means since it's uranium, then it's going to have the same atomic symbol and the same atomic number. Remember, atomic number, that is the number of protons. And that defines the element. If I am a carbon atom, so I have the elemental symbol, of C for carbon, then that means I always have 6 protons. If I have 7 protons, I'm no longer carbon anymore. So it's basically like it's DNA. It's what it defines it. But up top here, we have the mass number. And this is the number of protons plus the number of neutrons. And those are what's found in the nucleus. Mass number is denoted by the letter A. The atomic number is Z. And the symbol is the letter of the abbreviation. So when we have nuclei changing, this happens spontaneously. And when that happens, it emits radiation, which is why it's called radioactive. These nuclei that are changing, we call these radionuclides. They're the radioactive particles that are involved in these types of reaction. When we balance these equations, so when we balanced regular equations before, we just dealt with mass. We're still going to do that here. And remember when we did electrochem, we dealt with mass and charge, but we're going to do that here too. So we're going to write these nuclear equations. We're going to balance mass number as well as atomic number. So rather than coefficients out front, we're going to be dealing with what's happening inside the nucleus. So the first one we're going to talk about is alpha decay. Alpha decay is the helium nucleus. So it is and it basically has the exact same formula as helium, with 4 as the mass number and 2 as the atomic number. So 2 protons and 2 neutrons. So this happens when we have a nucleus that is unstable because it has too big of a mass. So we need to start to reduce some of the mass to help it feel more stable. So the parent nuclide is what is our reactant, and our daughter nuclide is the element that comes out. Not the radionuclide, those subatomic particles that come out, or in this case, a radioactive particle, helium, but the resulting product that's still an element. So here we have uranium decomposing into, or decaying into thorium, and notice the mass number and the number of protons went down and helium is out. So when I balance this, I need my bottom number, my atomic numbers, to add up on both sides. I also need my mass numbers to add up. So here I had 92 protons going to 90 in thorium and 2 in helium, so that's balanced. For mass number, I have 238 in the parent, and then 234 and 4 for the daughter nuclides. So helium nucleus is always going to come out with these alpha particles. This is most ionizing, but the lowest amount of penetration into different objects. So to be protected from alpha radiation, you basically can just have paper or a light cloth. So like your clothes would be sufficient at blocking this type of radiation. But it's ionizing because it comes along with the charge of a proton is +1. So if I think about charges, we don't actually write like legitimate charges on these types of reactions. So for this particle, it has 2 protons and 2 neutrons. Well, protons are positive 2, so this comes with a positive 2 charge, right? It doesn't have the electrons around it. And so it can actually cause if it hits into something, it can cause something else to become an ion because of that charge. So when something loses an alpha particle, its atomic number goes down by 2 for those protons, and then the mass number also goes down by 4 because of the 2 protons and the 2 neutrons that are involved in it. So with beta decay, this happens when we have a nucleus that has too many neutrons. Okay, so it's neutron heavy. So what happens is a neutron, right, has a mass number of +1, but no, it's not a proton. It transmutates into a proton. So the neutron literally turns into a proton, which means, it has a positive 1 charge, and it's the size of a proton. So then we don't have our subatomic particles or our different numbers balancing. So in order to balance it, we need to lose what we call a beta particle. So it has a -1 charge and no mass. And we notate it like this. So a nucleus or a neutron turns into a proton, and it emits one of these beta particles. And they're kind of like an electron because they're the size of a proton, but they're just the opposite charge. So that's why it's very similar to that. This penetrates more because it has a lower mass, so it can penetrate into light cloth, but you can be protected if you wear heavy cloth. So it can still get further into materials. And so when we lose a beta particle, our atomic number goes up by 1, but the mass number stays the same. An example of this, if I have iodine 131, iodine has 53 protons and 78 neutrons. But because of that, we'll learn why it's too heavy in a minute, but it ends up turning into, so if it loses a beta particle, let's try to figure out what the resulting daughter nuclide is going to be. So notice my mass number doesn't change here, so I'm still going to be 131. But I need to be 1 higher. So I'm losing a negative charge. So in order to be 53, so we could just kind of think about it like 53 equals x plus and then -1. So to get x by itself, I'm going to add 1. So x, our resulting thing, is 50. That should be add 1. 54. So I'm going to go look on the periodic table. Who is the 54th element? And it is xenon. So that's how I find out the atomic symbol. Okay. So the next type of decay or emission we're going to talk about is gamma emission. These are high energy photons. So these are actually not, well, they're a particle just like any other photon could be a particle, but they're high energy, low mass, right? We don't think of gamma or any type of electromagnetic radiation as having mass. We think of it as light. So we don't actually lose any particles from the nucleus. Our mass doesn't change at all. So this actually happens with other types of emission. So let's say we have a beta particle, beta decay, then a gamma particle might also come out, but it wouldn't affect the balancing of the equation. So for example, so we notate it as our gamma particle as this symbol, that's gamma. And the way we put it in a chemical reaction is like that. And yeah, it's just a little packet of light. So these are the most penetrating because it's just light. So to protect it, you need lead plates, cement walls, right, that are really thick. So that's how we have to break or block these. Yeah, and so we'll still have the same type of particles. So with positron emission, it's kind of like beta decay, where I'm going to lose something that looks like an electron, but it has a +1 charge. It's the anti-electron. Sometimes people actually call it beta plus, like that. Yeah, so they're very similar to those beta particles. And when this happens, basically we have too many protons in the nucleus, and so we need to convert some protons to neutrons. So this one's when we're proton heavy. So I'd have a proton, and it emits a positron. And it turns into a neutron, which has, a 1 up here and no charge. An example of this is if I have phosphorus, 30. So phosphorus has 15 for its atomic number, and it's going to release a positron here. Okay, so the resulting daughter is going to, notice the mass isn't going to change at all, so I'll still have 30, but my atomic number, I lost a positive one, so it needs to, both of these need to add up to what I have on the other side, 15. So 1 plus blank equals 15, well that's 14. So we could go look up what the atomic symbol is, and this is a silicon. So we lost our mass number stays the same, but our atomic number is going to decrease by 2. So electron capture is where an electron from one of the inner orbitals is pulled into the nucleus. And we don't actually emit any particles, but we're still changing what our element is, because the electron here is coming in and basically turning one of the protons into neutrons. And we've seen this before with positron emission. So here I have a proton, and an inner orbital electron comes in. So notice my mass number is going to stay the same, and I have a positive 1 plus a negative 1, and that gives me 0. And so a particle that has no charge and is a positive 1 for mass is a neutron. So notice a proton turns into a neutron. An example of this is rubidium-81. And if I add an electron into it, I have 37 minus 1, so that's going to turn me into element 36. That is krypton, and my mass number will stay the same. So atomic number decreases by 1 and still have the same mass. Here is a nice summary sheet of what changes when we have a reaction. We'll notice the neutron to proton ratio. We'll talk about that soon. And then we have some examples of each one. So let's practice writing these decays. I want the alpha decay first of radon 222. So I have, we're going to write radon 224, and we want to look on our periodic table to find the atomic number. This is in spot 88. And if it undergoes alpha decay, then I'm removing 4 from my mass. So I'm going to have a mass number of 220, and I'm lowering my atomic number by 2. So I'm going to end up being 86. So element 86 is radon. So radium turns into an alpha particle plus radon 220. Okay, for B, we have beta decay of berkelium 249. So berkelium, if we go look at the periodic table, is in the transition metals, F block, number 97. If I have a beta decay, that's basically an electron. So I'm going to have a higher atomic number, so that'll be 98. And then my atomic number will stay the same. 249. So that turns me into californium. For C, I have positron emission of oxygen 15. Oxygen is number 8. So if I have positron emission, that means, it turns into a positive electron. And so I'm going to lose a charge, so I'm going to become number 7, but my mass will stay the same. So number 7 is nitrogen. And then electron capture. So I have iodine, 111. Iodine's mass or atomic number is 53. So if I have electron capture, I'm going to add an electron. And that's going to turn me into, so negative, I got to lose a charge here of a proton. So I'm going to go down to 52. But my mass number stays the same, so 111. And 52 is tellurium, Te. Okay, so this is an overview of the types of decay. Now we're going to talk about how do we know if it's going to do an alpha or a beta or a positron? How do we know what's a good ratio for a nucleus to be?